We finished up Bohr's theory in the last lecture, and we ended up with equation En is equal to minus m of z square 8 epsilon naught square h square 1 by n square. This was one of the energy equations. Then we find also radius and all those. We saw the hydrogen spectrum, its origin, and in this case, while deriving the Bohr's theory or the expression from the Bohr's theory, what we assumed that this nucleus is heavy of infinite mass, and but in practice or in practically it is not so. We practice it is taken to be finite. So the nuclear mass is actually finite. So we take a finite nuclear mass and we approximate the equation, an above equation, this. So when we take this finite mass of the nuclear, if suppose that m is the mass of the nucleus and m is the mass of the electron, then you can write that En will be equal to minus of mu, not m, where mu is called reduced mass, and it is given by m divided by m plus m, where this m is mass of electron and this is mass of nucleus. If you see it more thoroughly, this expression, you will find that this mu is slightly less than m. The electron energy is then what happens actually? This gives us that the electron energies levels, the electronic energy levels or electron energy levels are slightly less negative. Because this becomes smaller than this. Sorry, not this here, this mass. This. That mu becomes smaller than m, not by large proportion, but by a small. This mu is less than m. And this, so it gives us this En is less than En when we take mu, reduced mass. I have taken mu here when we take reduced mass. So energy levels are slightly less negative than the earlier approximation, where we have chosen that this mass is infinite. Another thing is that this means that when energy is small, your lambda will be large, the wavelength of spectral lines. So lambda for spectral lines is large as compared to slightly larger than those which are when we take infinite mass of the nucleus. Then there are further modifications to Bohr's theory. There are some limitations to it. Then that probabilistic interpretation. Then Sommerfeld theory. So Sommerfeld modified the Bohr's theory. I will not go into the detail of the Sommerfeld. Rather, I will give you this assignment. That is Wilson-Sommerfeld model of atom. This is for you people to do it. So Wilson-Sommerfeld plus Bohr's theory. So he modified actually Bohr's theory. So it is called a Bohr-Sommerfeld theory sometimes. So what are the modifications which he has done in this case, and what are the results which he obtained? So it is for you people to do and study this part. Then we will move to the next topic.
सर ये आपको सेंड करना है कि खुद से पढ़ना है?
आप इसको पढ़ो, मैं पूछ सकता हूँ इसके बारे में कभी भी कुछ भी, इवन कि आप ये एग्जाम में भी आ सकता है। फिर जो असाइनमेंट में देता हूँ एग्जाम में भी आ सकता है। Now, the next topic is which you have already studied this. Most of times you have done it in BSc classes, then in the quantum mechanics as well. But we will briefly review it here. That is the quantum numbers. I think Nyasab has made it fully understood to you people. क्योंकि आपने quantum mechanics में पढ़ा होगा ये. Quantum numbers. We have to review these quantum numbers. So, if you see Bohr's theory, En, when you find the energy of the nth orbital, that is minus mu z square E4 divided by 8 epsilon square. This epsilon not actually for vacuum, 1 by n square. And you find that this n is 1, 2, 3. It is a integer, positive integer. And E varies when we really change the value of n. That means we change the particular energy shell or the energy level actually, as per the Bohr's theory, energy orbit actually. These were called the orbits. So n equal to 1, 2, 3, these are the positive numbers, positive integers, and this n is one of the quantum numbers. So these, if you see that these quantum numbers, actually they accepted this n was derived from Bohr's theory, but this n has been also found to be valid when you solve Schrodinger equation.
Yes.
Schrodinger equation for hydrogen atom.
Yes.
So these arise actually, these quantum numbers arise during search for an acceptable solution of Schrodinger's wave equation. Schrodinger's wave equation. When we search the solution for Schrodinger's wave equation, then some quantum numbers arise like L or ML values, which L, mostly L arises from there. We will see that from the radial equation of the hydrogen atom. And in case of N, which is called as total, it is also called as principal quantum number. And the values of En, that is what is this called as eigenvalues. Eigenvalues depend only this on n. If you see in this equation here, these depend on n. So when we vary this n, we will see a change in the energy. So according to Schrodinger equation, or as per the Bohr's theory, this n has the same meaning. So we will find the same value of E and En, which is obtained by Bohr's theory, and if you obtain it by from Schrodinger's equation, wave equation. So n also signifies the quantization of total energy of the atom. So it also signifies the total energy of the atom. That's why it's called sometimes total quantum number or principal quantum number. This is simply, and remember that quantum numbers actually, they are particular address for an electron of an atom. So quantum numbers actually, if you want to understand what the quantum numbers signify, so quantum numbers, they represent a particular address. Like we have an address for our houses, house number, then village, street, then tehsil, district, and all this. So same is the case with electrons. So we need to locate it. So we locate it by identifying it as quantum numbers. So there's an address for a particular electron. So how to find an electron of an atom? So we use quantum numbers for that. And n is one of first quantum number total. Then if we see that there is another quantum number which is called L, that is orbital quantum number. Orbital quantum number. And if you see the orbital quantum number, it originates from the radial equation of hydrogen atom. You have all studied this hydrogen atom, and I will not go into the details of this. And if you see the radial equation, 1 by r square ya çekmiş, başta çıkamaz.
Yes, or L of L.
Where we have energy E here. So energy E will be total E total. It will be kinetic energy plus potential energy, that is K, and this K has two parts, kinetic energy. The kinetic energy has two parts. One is it has two parts. One is radial part of the kinetic energy due to electron motion towards or away from nucleus. It is just like this. This is the radial part, so towards or away from the nucleus. And another one is the due to orbital motion of electron. So the kinetic energy part has two contributions. One is from the radial motion of the towards the nucleus, towards or away from the nucleus. Another one is simply the motion of the electron in its orbit around the nucleus. Then we can write E total is equal to K radial plus K orbital plus V of R, which is the potential energy. And in the radial case, if you see the radial case, if we put up this value in the radial equation of the hydrogen atom, we will get that the radial equation of the hydrogen atom becomes 1 by r square d by dr of is K radial, K orbital plus V of R, and minus this V of R will cancel out. Then I will cancel it. So minus here h square by 8 pi square. I have taken common actually here h, this 8 pi square by mu, then multiplied here. It's reciprocal to balance the equation. Sorry, this is L into L plus 1. Is equal to 0. Now, since it is a radial equation, so we will not consider it as it will be free from the orbital part of the kinetic energy. It is a radial equation, and this is possible only if the last two terms, these last two terms, this K orbital plus this, they cancel each other. What I mean to say is that this radial equation, since we have radial equation, and radial equation must be free from orbital part or orbital kinetic energy. So this is possible only if last two terms, that is K orbital, will be equal to h square by r square, if this condition satisfies. Then only we can get rid of the orbital part here. And we know that L total, it is orbital, it is angular momentum simply, not orbital. We'll take angular momentum. L is an angular momentum, and let up for an electron, then we know that L is equal to mv r. I can write it as mu v r because of the reduced mass in case of an atom. Now k orbital will be equal to 1/2 of mu v square, that is all L square by 2 mu r square, just using this equation here in this case. So L is equal to mvr, so that's mu vr. So for B, I am putting this equation L by mu r, and it is mu r square. One mu will cancel out with this mu. I can write then which is equal to L square by 8 pi square mu for orbital part here, this k orbital. So this k orbital. So I'm equating these two, and if you equate this, you will get that L square is equal to L into L plus 1 h square by 4 pi square. When you further h by 2 pi, this is how you end up with the angular momentum of an electron in terms of the L, this L. And this is a quantum number. This is called orbital quantum number. L, and it is restricted to the values L equal to 0, 1, 2, up to n minus 1. So n is the principal quantum number. So for example, if n is not equal to 0 actually, n is equal to 1, 2, 3, 4, etc. Your L will be 0, 1, 2, 3, because it is n minus 1 here. Then this becomes S, P, D, F, G. These are the orbitals, the orbital quantum number. So we also know that electron can have only discrete values. L, that is angular momentum, that we have already seen from the postulates of Bohr's theory, NH cut. So the orbital angular momentum then becomes quantized. L becomes quantized. And when it is quantized, so it is determined by the this L, small l, orbital angular momentum or orbital quantum number. So for example, if n is equal to 3 and L is equal to 0, sorry, or L is equal to 0 or L is equal to 1. When n is equal to 3, L is equal to 0, it becomes 3s. When n is equal to 3, L is equal to 1, it becomes 3p. When it is 3 and L equal to 2, it becomes 3d. Here, d. Okay. So this is how we name those orbitals in which the electron can be found by probabilistic interpretations. One more is there, which is ML. Up to now, we have seen that we are generally talking of an electron who is in the field of an atom, nucleus, or the other atoms. That means there is a nuclear field, there is the other atomic fields. We have ignored the other effects because of other atoms, but we have considered that there is a field because of the atom coulombic field. And these quantum numbers, they are not interfered by external forces or external field, N and L. But ML is the quantum number which arises because of the interaction of the atom to the external magnetic field. So ML arises actually just due to interaction of atom with external magnetic field. So when we place an atom in any external magnetic field, we have then this characterize or specify the particular position of an electron or particular value of the electronic energy by the ML values. And we know that since atom, this electron, it revolves, or it has a, if we assume the Bohr's theory like planetary motion, if we assume Bohr's theory, according to Bohr's theory, or it is continuously moving around the nucleus. So when a charged particle moves, for example, it moves in this direction, E, this circular path, it becomes actually a dipole when a charged particle moves in a circular orbit. So when charged particle is moving in a circular orbit, it forms actually a dipole in this. How? If there is a ring, circular ring, copper, and there is some current going on it in this copper ring, then on the one side of the copper ring, you will have a one polarity of the magnetic field. On the back side of the ring, there will be another polarity. Do you understand what I mean? For example, if this is simply a
Yes, sir.
so there is a motion of this electron like this. So there may be a one polarity. For example, it will form as a south pole of the magnet. On the opposite side of this ring,
South Pole.
there will be a north pole. So it will be actually,
North.
if it is going anti-clockwise in the upper part, upper surface, on when you see it from the opposite side, it will be in a clockwise direction. You will see in a clockwise direction. So it just,
North.
yeah, it just forms
सर मुझे आवाज नहीं आ रही है साफ.
Insha.
जी सर.
Okay, I think network का कुछ issue हो सकता है, but if there is any, किसी और को भी कोई problem आ रही हो तो मुझे बता देना. अभी सुन पा रहे हो?
जी सर अब आ रही है साफ आवाज.
चलो ठीक है. Okay. So that means an electron which is having an orbital motion in a particular orbit forms a magnetic dipole. Simple. This is the simple concept. Orbital motion of an electron. So when we have an orbital motion of an electron, this forms an magnetic dipole. Sorry, not electric, it's a magnetic dipole. Sorry. So we have a magnetic dipole. So that means when we have a magnetic dipole like this, north south, where it is from south to north dipole moment like this, then it has a dipole moment. So there's a dipole moment then for a dipole, and dipole moment signifies the strength of the dipole. Actually, this is an important parameter which we need to take into consideration when we are discussing dipoles, whether it be an electric dipole or be it a magnetic dipole. So for a magnetic dipole, we have a magnetic dipole moment, mu, and this magnetic dipole moment is important. Now, when we place any dipole, for example, if this is a magnetic dipole and I place a external magnetic field here, and I can write X, Y, Z, then this is the B direction here. Sorry, this is the dipole. It is, I can write dipole moment as mu B, magnetic dipole moment in this direction, and I apply some field B here in the Z direction. Since this is the motion of the electron, which is like this in the circular orbits. And when this is the case, then what happens actually, your L in the direction of Z orbital quantum number, orbital angular momentum, which has a component, its component Lz cos theta actually, and the Z direction, this becomes quantized and it is denoted by MLH cut. It has different values in the external magnetic field because the dipole will interact with the external magnetic field, and that external magnetic field will try to align this dipole in its direction. This is the effect of external field on any dipole, like be it an external electric field to an electric dipole, yeah, magnetic dipole in the magnetic field. So what the external field will try to do, it will try to align that dipole in its own direction, like this. So if I have this, so it will try to align this direction, this dipole in this direction, and there will be an energy which will be stored in this dipole, magnetic potential energy. And this magnetic potential energy, it depends upon the magnetic moment of the dipole and its orientation. So I will repeat it, that whenever we place a magnetic dipole in an external magnetic field, the effect of the external field is that it will try to orient or align the dipole in its direction. So since we have a dipole moment is a vector quantity, so it can be resolved into its components. So one of the components which is in the direction of the magnetic field will be given by Lz, and it is given by then MLH cut. And while doing this, there's a magnetic potential energy which is stored in the dipole, and this is equal.
आवाज नहीं आ रही है.
Okay, so let me change the network. Can you hear me? आवाज आ रही है?
Yes, sir.
Yes, sir.
Okay. So what I am saying is that if any dipole is there, electric or magnetic, when we place it in external magnetic field, it will try to align this dipole, external field will try to align the dipole in its direction. That means if this is the B here, so it will try to align this dipole in the same direction. I think you know the reason how it is possible. So this is from north to south. This is from here north to south. So I think yes, south to north. Dipole moment has a direction of this, and this is north to south. So there will be some force of attraction between. There will be repulsion. There will be again here repulsion, and this will be attraction. So finally, it will be dipole will try to orient in this direction, and dipole will move like this, south to north, and this is the direction of dipole, P, the mu B, dipole moment. So dipole moment will be oriented in the direction of external field. And we also know that we have an orbital angular momentum and the dipole moment, which has a vector, which is a vector quantity orbital angular momentum. This orbital momentum vector will have its Z component, which is in the direction of the magnetic field, one of the components. So if it is, if for example, we have a dipole this or L, direction of L like this, it has a component, one is, so you resolve it into components. So this is the cos theta component, sin theta component, sorry, this is the cos theta component, if this is the theta with this. But if you have for example, this is B and this is your some dipole moment and it makes an angle theta. So you resolve this into its components. So one component will be in this direction, then yes, you take the different components of this L, and that is Lz in this direction. So we specify that this Lz in terms of ml h cut. So what does it mean? It means that the direction of L is quantized with respect to external magnetic field. That means it can take particular values of L in external magnetic field. We cannot say that it can have any value, but it takes the values of uh, integral values, like Lz is equal to ml into h cut, where ml has the values L minus 1 through 0 to L plus 1 through 0 to L minus 1 minus L minus 1. So I can write R, it is 0 plus minus 1 plus minus 2 plus minus L. And this ml describes the quantization of the orientation of L in magnetic field. This is called as, when we quantize L, orientation of the L in external magnetic field, this is called as space quantization. So it's called as space quantization. For example, if this is the B and this is L here, so we can have here L values, different values of L, like this. Then you find values like this. They're equidistant. We will study more about these when we study the Zeeman effect and all this. It will be studied in detail there. This is just a review of this ML originates. So this is, if this is the suppose that this is 0 for ml equal to 0, this is ml equal to minus 1, and this is plus 1 plus 2, this is minus 2 here. So this is, sorry, this is Lz vector, this. So this becomes minus 2 h cut, this becomes minus 1 h cut, this becomes 0, this is 1 h cut, 2 h cut. These are the values of Lz, and this is called the space quantization. So it can actually, this L, what does it mean? It means that the orbital angular momentum vector L, it precedes around the external magnetic field B, this, and it forms a cone. So if this is an B, the L will like this. So it is called as, it is also called as magnetic quantum number. Remember that ML is the magnetic quantum number. And it gives actually the quantization of the magnetic energy of electron, because the electron gains an energy in the external magnetic field. So it is also called as quantization of the magnetic energy of electron. That is why it's called, sometimes it's called as magnetic quantum number. And from all this, we can see that each of the eigenfunction of one electron atom, that can be specified by these quantum numbers, M, L, ML. And we know that what these are actually.
Sir,
हाँ बोलो.
सर जो L होता है वो always z direction में होता है.
Actually हम Z इसलिए consider करते हैं because we are applying the external magnetic field in that direction. Actually it is not the Z direction, it is the direction of the magnetic field. Okay, and we assume that we are applying the magnetic field in the Z direction. It's not always, you can take it in any direction, but the most of the these simplifications are done along the Z direction, and Z is taken generally like this.
it means it will also along x and y axis.
Yeah, you can. It depends on in which direction you are applying the magnetic field.
Okay, sir.
Okay, in that component is quantized actually. The direction in which you are applying the magnetic field, the component along that direction is quantized.
Quantized.
Okay.
Okay, sir.
So this is, I think, all for today.